Hi, and welcome to another video on shear turbulence. We're working our way through common locations where shear turbulence is found. We've gone through surface friction and KH waves. We've talked about temperature inversions and fronts. Now we'll look at jet streams and the shear that's associated with them.
So here are some of the topics we're going to talk about. First, we're going to define exactly what is clear air turbulence. And there are a lot of different definitions depending upon which textbook you use. Here's one that's kind of general. It's turbulence that happens near the jet stream. And usually up there, there's not a lot of clouds. However, there are some cirrus clouds. So, the term clear air turbulence sometimes is a misnomer. Here's another definition. This is straight from the Glossary of Meteorology. It says it's turbulence that happens at high altitude, usually in clear cloud-free zones or cloud-free regions, but it is associated with wind shear, and you'll find it in upper fronts and tropopause. Remember those two common locations of clear air turbulence. We're going to be spending a lot of time talking about those. Now, before we get into clear air turbulence, we've got to talk about a few concepts that you may have seen before. We're going to look at jet streams and how we describe jet streams, and then after that we're going to talk about the tropopause. So first, jet streams. Here's a cross-section of a jet stream, at least an artist's version. That area that's colored green is the jet stream. And a jet stream is any region of fast-moving winds, narrow region of fast-moving winds in the atmosphere. Jet streams happen a lot of different places in the atmosphere. You'll also find jet streams at low altitudes, believe it or not, but not as strong or not as great as the jet streams that you find in the upper atmosphere. Jet streams in the upper atmosphere typically exceed 100 to 150 knots. The FAA defines a jet stream as 50 knots. If you look at aviation weather, anything more than 50 knots, they consider a jet stream. The center of the jet stream is called the core, and that's a three-dimensional representation of the jet stream, the maximum or center of the winds, the fastest winds moving along. If you look at it three-dimensionally, you can call that the core. And in this figure, the core is shown with the red arrow. In this case, the wind is blowing from the west to the east. You could see the arrows representing east and also north. So in this case, and in most of our examples, we're going to be talking about a jet stream that's moving from the west to the east. There's another term, a couple other terms that we use. Jet streaks is another term that you may hear. And jet streaks are winds in the jet stream that are moving a little bit faster than the surrounding jet stream. So it's a concentrated region of fast-moving winds, and they move through the jet stream. As you know, the jet stream moves around the world, and in the jet stream itself, there are little regions that are faster than the surroundings.
Another term that we use is the jet axis, and by definition, the jet axis is the axis of a maximum wind speed in the jet stream. If you connected on a chart the points with the highest wind speed, you'd get a line, and that line we call the jet axis. In this figure, you can see that really there are a couple jet axes. There's one that kind of goes to the south, but then there's an area of stronger winds, faster winds a little bit to the north that kind of pick up there. Not sure if they split off, the jet axis splits off, or it's a separate jet axis, but you'll see that sometimes. Another term that you should be familiar with is isotachs. Isotachs are lines of constant wind speed. So isotachs typically are colored to indicate the strength of the wind. In this diagram, you can see in the bottom there's a key, and they start to color the isotachs at 40 knots with yellow, and then starting at 50, you can see it changes color to kind of tan, and it just goes up from there. So each one of those different colors represents an isotach, and in that region the wind speeds are that wind or greater. And we use isotachs to help us figure out where the jet stream is. This is the world, believe it or not, up at 250 millibars. So they are coloring areas where wind speeds are greater. It looks like they use kind of magenta and purple and red to indicate the fastest winds in the jet stream. And green, probably weaker, maybe about more 50 or 70 knots. This was taken in June. So this picture or this chart, you can see in the northern hemisphere, the winds are a lot weaker, but in the southern hemisphere, the winds are a lot stronger. And that's what you typically find during the summertime in the northern hemisphere would be the winter in the southern hemisphere. And in your winter hemisphere, the jet stream is always stronger, meaning the intensity of the wind. It's faster in the winter hemisphere. So that brings us to our next topic, which will be the tropopause.
A couple other terms you need to be familiar with. The tropopause. Tropopause is the boundary between the two lowest layers of the atmosphere, the troposphere and the stratosphere. Troposphere is the lowest layer of the atmosphere. As you go up through the atmosphere, temperature decreases in the troposphere until you get to the tropopause. At that point, the temperature may be constant or may even increase a little bit as you go into the stratosphere. So tropopause is just the break between the troposphere and the stratosphere. In a standard atmosphere, typically the tropopause, it says here, about 36,000 feet, but it varies with the time of year. Typically, in wintertime, the tropopause is a lot lower, and during summertime, the tropopause is a lot higher when the temperature of the air is much warmer. And if you go north or south, tropopause also varies. Typically, lowest tropopause are found near the North Pole, and the highest are found near the equator. Also, another important fact about the tropopause, it's the coldest temperature that you'll find in the lower atmosphere. As I mentioned, the lapse rate changes, and because the lapse rate changes, in other words, the temperature profile changes, the tropopause is a very stable layer of air. And the tropopause acts as kind of a lid or a cap to the jet stream. It sits right on top of the jet stream. In this figure, I've colored the jet stream green, the jet core red, and then the tropopause is kind of a purple color. So the tropopause sits right at the top of the jet stream, or at least the jet stream core. Also notice how the jet stream or the tropopause, as it comes over the jet stream core, it drops down to a much lower altitude to the north. And that makes sense because to the north, the air is much colder and the tropopause is lower. To the south, the air is much warmer and the tropopause is much higher. So you can think of the jet stream as acting as a separator between warm air and cold air. Warm air to the warm air to the south and cold air to the north.
Here is a SKU-T log P diagram and also a 300 millibar chart. The SKU-T log P diagram shows in red the temperature profile of the atmosphere as measured by a radiosonde. This radiosonde ascent was made over Gray, Maine, which is highlighted with a circle on the 300 millibar map, and it's very close to the jet stream. Looking at this, you can see that temperature decreases with height all the way up to the tropopause, and then above the tropopause, temperature is constant or decreases more slowly. The 300 millibar map also shows a strong jet stream, and that is evident on the SKU-T log P diagram. Looking at the wind barbs that are on the right, I've highlighted those in red. You can see that the winds increase all the way up to the tropopause, probably the strongest right below the tropopause or right at the tropopause, and then start decreasing with height. We are now going to look at a two-dimensional representation of our atmosphere and the jet stream. Normally we look down as on a weather chart. And now instead we're going to look at a different perspective. We're going to look at a cross section, meaning going from north to south and then up. The cross section that we're going to look at stretches from point A to point B on this 300 millibar chart. Point A is in the cold air over Canada. Point B is over the Atlantic Ocean just off the coast of Florida in the much warmer air. In between, you can see a very strong jet stream and also a jet streak that's moving across New York and also New England. This is the cross-section of the atmosphere from point A to point B. Notice that it's very colorful. Those colors indicate isotachs, and isotachs are lines of constant wind speed. In this case, the calculation that was done was a computation of the wind component that is normal to this cross-section, meaning that the winds are blowing into or out of this page. Specifically, since A is north and B is south, then the winds typically in the jet stream blow from the west to the east, so in this case they would be blowing into this page. This is a conceptual model of a cross-section across the jet stream. It's very much like what we just saw in the previous picture. However, it's simplified with green lines indicating isotachs. The red area is the strongest winds. That is your jet stream core. The winds in this picture are moving into the page, so that would mean that the winds are from the west moving to the east, with colder air to the north and warmer air to the south. Also notice that the isotachs are changed very rapidly or packed very closely on the north side of the jet stream. As you move to the south, the isotachs are farther spaced apart, which means that there is stronger wind shear on the north side of the jet stream.
If we take away the isotachs, we can see some structure to the atmosphere. You'll see the two tropopause. One is tropical because it sits over warm air. The other one is the polar tropopause because it sits over colder air. And then that black double line that you see going from the ground up through the atmosphere is actually the front. And jet streams and fronts kind of coincide. They go hand in hand. Usually when we're looking at fronts, we look at the lower part of the front from, say, about 10,000 feet and lower. But if you go throughout the atmosphere, you'll see the front actually connects into the tropopause and it wraps around the jet stream. That upper portion of the front we give a special name. We call it the upper front. And upper fronts are very important because they're locations where you'll find clear air turbulence.
Now that we have an understanding of the structure of the atmosphere and all the different phenomena that occur, the jet stream, the upper fronts, and tropopause, we're going to use that to gain an understanding of where turbulence is generated in our atmosphere through shear.
So, speaking of clear air turbulence, what kind of requirements do you need for turbulence? Shear turbulence requires stability and, of course, wind shear. We talked about stability, how stability holds back the turbulence until the shear gets so strong, and then it breaks through and overcomes the stability. And this video shows how shear turbulence forms, and this is what's actually happening in the upper atmosphere. You've got winds that are moving actually the same direction but different speeds. That's the jet stream, and that's the strong shear associated with the jet stream. As that shear propagates, it produces a wave. The wave breaks, and that breaking wave produces lots of little eddies, which is turbulence. So this is what's happening in upper fronts and also in the tropical tropopause, because that's where you find the strongest stability in the tropopause and also in fronts. We talked about how fronts are very stable regions, and also the tropopause is a very stable region. So you also find the strongest shear in the atmosphere surrounding the jet stream, on the north side of the jet stream, and also above the jet stream. As you go above the jet core, you can see the winds decrease very rapidly with height, with the packing of the isotachs. So above the jet stream core is where, in the tropopause, is where you find really strong shear. And in the upper front, on the north side of the jet stream core, in those two black lines, the upper front, is where you find the strongest shear.
Now that we know the locations where we can find strong shear associated with the jet stream and also up in the tropopause, We'll use that knowledge to figure out where clear air turbulence is most common.
So those are the locations where you find the strongest clear air turbulence: above the jet stream core in the tropical tropopause, and in the upper front, that is just to the north and below the jet stream core. That's where those two conditions are met: strong shear and strong stability.
So that's a little bit about the theory of clear air turbulence, the shear turbulence that occurs around the periphery of the jet stream, and the locations where you'll find it. In the next video, we'll cover clear air turbulence, and we'll go through a little bit of flight planning exercise, and also we'll talk about how to fly clear air turbulence and how to avoid it. And once you do experience it, what should you do? So stick around.